There, kids.
It's 3.4 notes, properties of logarithmic functions. These are some really handy properties.
Handy indeed.
And they have to do with the rules that we have with exponents. So
yes.
Can I go over those
real
quick?
Yes, please. Let's just touch some bases with those exponential rules.
So I'm just going to use a generic letter A and some generic other letters. Let me start that letter over. Okay, if I have A to the M times A to the N, remember that we can add those exponents together because of the fact they have the same base. We can just add the exponents together. So this would be a case like where you have x squared times x to the third equals x to the fifth.
Right, because 2 plus 3.
Yeah, yes. and that's the product rule. The quotient
The pro rule. Is this going to be the quo? The pro quo.
Is that if we have them being divided, instead of adding the exponents together, we subtract them. And so that's like where you cancel things out, right? Like x to the 6th over x to the 4th is
x squared.
X squared. And then the power rule.
I've got the power.
Yeah, exactly. The power rule.
You probably don't even remember that song.
No, well, remember it? Probably not. I know the song. Yeah. Is where you have something and then it's raised to a power. And so you multiply those two things together. Okay,
there you go.
So those are our exponent rules, and they are connected to these logarithmic rules because logarithms and exponential functions are related.
They're inverses.
They are.
They're inverses,
yeah,
Steve 320.
That's so true. So if you have two things inside of this parentheses for your logarithm that are being multiplied together, you can separate those into two different logarithms where you add them together.
Right.
So you have to remember that multiplication and addition go together for this rule.
Right. And multiplication and addition go together anyway.
Yeah, in general, those things should make sense that they go together. If we are dividing R divided by S, we can split those into subtraction.
Because oftentimes division and subtraction go together.
Yes, they do.
Yes, indeed.
And this says R to the C. It looks a little funny, but that's like R raised to the C power. Yeah. What you can do is you can move that in front of what you've got going on there.
Right. So now that is a little bit of a trickeration rule. That's not one that we would normally think of.
Yeah, I don't know. To me, it just makes sense because like if I've got maybe this situation going on, I just think of it like that exponent's not really attached, so it gets to float up in front or something like that. Right. But however you need to think about it is fine. We're going to prove one of these.
Oh, my goodness.
What did you do to my colors?
Okay, choose crayons. Choose to the right.
Oh.
Right there.
Okay. My crayons were gone. Okay, so we're going to prove the product rule. So here's what we're going to do. We're going to start with a little bit of substitution. Now,
how come we're substituting right off the bat?
Because that's what we're supposed to do.
Okay, if you say so. I believe you.
I'm gonna be on. Can I be real right now?
Yeah.
Okay.
Are you imaginary?
No. Maybe. Ow, that hurt. Don't do that.
You felt real.
Don't do that. Okay, so I found this proof tricky. I actually had to look it up. And so this is not something we would expect you to do on your own. But it is kind of interesting to see, well, why is it that this is really true? How do we know that this is true?
Let's do it. Is this part of your master's work that you came across this? Highfalutin mathematical
No, I looked it up in our book.
Oh, it's in the book?
Yeah.
Did you Google it?
No, it's in our book.
Okay, all right.
Okay.
Did you find it on Bing? Did you use Wolfram Alpha? You're going to ignore me now for the rest of this video? It's going to be a long time.
Actually, I don't think it will be. If it is, it's your fault. We're going to make this substitution. We're going to think about, let's let x be this first part. Let's let y be the second part.
And that's a good idea because those are different numbers.
Yeah, those are two different things. So we're going to let them equal separate things. And then we're going to think about what that means R times S would be.
Okay.
If we have R times S, no, I'm sorry, I skipped a step. Let's change these to exponential functions. So that would be b to the x equals r.
Right.
And b to the y equals s.
Right, because a logarithm is equal to its exponent. So if the base has to be b, then the equals part is the exponent.
Right. So now let's look at r times s. Because at some point, that's where we kind of need to get to. We need to get back to what is this that we're trying to show.
So R times S, we want to show an equality statement with this. So we would want to actually show what R times S would be.
Right. So R is B to the X, S is B to the Y. So let's multiply those together.
Since the bases are the same, I bet you add exponents. I'm just saying.
That is this product rule for things. So that's X plus Y. And that's still what R times S is? Oh, that's not an S.
That's the weirdest S I ever seen.
Okay, so now we want to continue trying to get this. So we're going to take the log base B of both sides of our equation.
Well, I have a log base B. Whoa. Okay, all right.
Okay, and that's something that we will talk about, especially in the next section when we're solving equations, that in order to get rid of this B on the right side, if we take the log base B of both sides, kind of like if you take the square root of both sides or things like that, you know. Oh, look at this property from 3.3 that shows up, the one where these are next to each other, they're the same, so they cancel each other out.
Another way to kind of think about what Mrs. Stevenson has just done is this is a new trick that you can put in your algebra pocket to help solve a problem. Instead of adding or subtracting numbers on both sides or square rooting both sides, you can now take a logarithm as long as you do it on both sides with the same base.
Right. So on the right side, we are just left with the exponent, which was X plus Y. The left side of our equation looks like the left side of what we were trying to prove. And the right side, X plus Y, is
what we
log
said.
B R and log B S. So let's just finish substituting in. So log B R plus log B S. And that's not necessarily a straightforward proof. It's not really anything like the trig identity proofs that we
But that's why it works.
But that's why it works, and you could do something similar for these other two properties as well to be able to prove that.
The other thing I wanted to point out here also is when Mrs. Stevenson took the log of both sides, you could just as easily have said that a logarithm is equal to its exponent. And so
that's true.
You could have gone right from blue to the purple with the log base B. That's your base.
I tend to forget about that step there.
And it equals the exponent. Well, my exponent was X plus Y. So both of those are totally legitimate ways to do this. It just depends on what your brain sees. And we obviously see things the same, but a little bit differently.
Yes, totally. Okay. Okay, example 2, we're going to look at expanding using the properties of logarithms to expand some things. So basically the way this works out is sometimes it's more helpful to have it as a bunch of different logarithms. Sometimes it's more helpful to have it as one logarithm.
Got to be able to go both directions.
Yes. So what you're looking for is things like multiplication, division, or exponents.
Right. What's happening here?
Nothing. Pay no attention to what was going on the screen. Okay. So think of this 8x y to the fourth. I was going to show them what buttons we were pressing, but whenever we get there.
Okay.
Okay, 8x y to the fourth. Think of that like it's multiplication, right? Because that's what's happening.
Right.
Okay, and so multiplication inside of a logarithm, you can change into separate logarithms.
Yes.
Yeah, with addition in between them. And that's that first property on our previous slide, the top of your paper. And then the other thing that we can do is anytime we have an exponent situation, we want to move the exponent in front of the logarithm.
We don't want anything up there.
So log 8 plus log x plus 4 log y. That is our final answer for this.
Yeah, it looks good. Now, always double check your bases because there may be an occasion where a number like 8 could reduce further.
Absolutely. If this had been log base 8
or log base 2
or log base 2, but 8 would be simpler to like log base 8 of 8 is 1.
That's 1.
So keep that in mind that could happen.
If it was a base of 2, it would have been a 3.
Yeah.
Figure that out?
Yeah. So now let's do the natural log of...
It's going to follow all the same rules.
Yes.
The reason it's going to follow all the same rules is because a natural log is still a logarithm. It just has a base of e. So nothing's different here at all.
I like putting parentheses around what's inside my natural log.
I think that's brilliant.
Okay. And then we are dividing here. So we need to separate the top goes in for the first one.
Top
and then
minus bottom.
Minus the bottom, right. And then on this square root of x squared plus 5.
Rewrite it with an exponent.
So we can put that, what exponent is the square root?
It's going to be a 1/2.
So
it's going to be 1/2.
That's, well, it depends on if I want to skip a step here.
Don't skip a step.
Okay.
Let's just show all the steps.
That's what I was thinking. X squared plus 5 to the 1/2, that's the same as the square root. And so we move the 1/2 in frontsies.
Right.
And, ooh, that's bright. 1/2 natural log x squared plus 5 minus the natural log of x. Now
that's it.
That's it, because, and you might accidentally try to keep going, but these are being added together.
Right, they're not being multiplied.
Right. If it was multiplication, we could keep going, but it's not. So let's stop there.
It's a good idea. It's a good stopping point.
Yeah.
All right. Backwardsville.
Yeah, so example 2, we expanded, and expand means to make bigger, and then now we want to condense. Condense means to make smaller. So typically these say in the instructions we want to write as a single log function. Also, in general, we want to go ahead and move things from in front of the logarithms to make them exponents. We're basically just undoing what we just
everything
did.
We just practiced, and we're going to go the other way.
Yeah. This is the natural log of x to the 5th, which I don't know why the 5 is there instead of in front of it, but that's whatever, minus 2 natural log of xy. The first thing we want to do is move the exponent. There is kind of like an order of operations here that it's safer to do this, right? Because you can't straight off combine these and then move the 2 unless you remember it's only affecting x and y.
That 2 has nothing to do with x to the 5th.
So yes, exactly. So this is xy, and that's squared.
Right.
And so I would like to think of that like x squared, y squared, personally. And that's a property of exponents, that both things inside are going to get that x squared, y squared.
To get into business.
Now we're subtracting, which means it changes to division when we write it as one logarithm. So that's the natural log of
x to the 5th over x squared, y squared.
Now I believe that we can simplify that.
I believe we can try.
X to the 5th over x squared.
That's a good one, thank you.
You can subtract those exponents.
Be here all year, children.
And get x cubed on top, y squared on. Every now and then your stupid computer hiccups.
I don't know why you would say that about my computer.
Natural log of x cubed over y squared. Maybe because it's a Mac.
You know, you're just jelly.
No, I'm not. Real quickly, before we start this example, most of the assignment, or about half of it, I would say, is expanding and condensing for 3.4. That's really the thing that we need to practice, because it's something that like they'll try to throw tricks at you, and you just have to learn how to deal with those tricks by seeing them. So the rest, though, this example 4 and example 5, they're pretty simple as well, and we're going to use our calculator to help us do some fancy logarithms. And part of this is going to depend on what kind of calculator you have access to, but all of them are capable of putting in
every single one,
any logarithm.
Yes.
Because of this formula called the change of base formula.
Change of base.
Which you need to know no matter what calculator you have, that the change of base formula is whatever the bigger number is.
Goes on top.
Goes on top, and the smaller number goes on bottom. And it's written right here with log base a of x and log base a of b, but typically we either use just the log button on our calculator.
Which is the base 10.
Which has a base 10, or you can use the natural log button.
Which is base e.
And that's the neatest thing about this, is that both of those give you the same answer.
The exact same.
Yes. So if you have an 82, an 83, or the updated OS.
The very old 84, yes.
Yeah, then what you're going to have to do is the change of base formula to plug this in. So you do log of 7, which this will open a parentheses.
Got to close. If you don't close the parentheses, then you're going to get some sort of really wacky number.
Yeah, we don't want that.
Yeah.
Divided by log base 4.
Yes. So.
And so if you look at your calculator, you should have already, hopefully by now, seen. Oh, this is not what.
Hey, that's a logistic function there.
A couple of them, actually, I think. Here's my log button. Or, hey, I could have used the natural log.
You could have yes.
They're created equal.
They are created equal.
So see what we got going on here. What was that, 4?
Yes.
And you press enter.
Yes.
We want at least 3 decimal places.
At least.
So
4 is usually a little more healthy with logarithms.
1.4037.
Yes, or 6. You can truncate. You don't have to round.
1.04.
Hold on. I got you. I got you just in case.
1. Oh, yeah, that's not what it was.
4037.
You started saying other numbers and it threw me off. Okay. Or if you have a calculator that's 84 plus with the updated version,
Math print,
you go to, if you can make fractions on your calculator, then you can.
You're gonna like what we. Oh,
cooler.
it's even. Oh no,
Yeah,
you're going a long
right.
way. You're going a long way. Get out of that.
Okay.
Alpha window.
Alpha window.
And then look, you're right there. Log base.
So that's the 5th option.
Option 5. Then bam, template right there.
Yeah. So we want a little 4, a big 7. We press enter.
Boom,
look,
same number. Hey, just for funsy onesies, do natural log.
Okay, I can do that.
Well,
Why not?
We could just take a tour. And by the way, notice that K-Steve is closing parentheses on that 7. I'm telling you that will get you every time.
All of those are the same. So that's super cool.
And handy.
Yeah, so now no matter what type of calculator you have, you can do any logarithm.
Any logarithm.
So you can go for it.
Which one you want? Which way you want me to do this one? And I'll just tune it up.
All right. It really doesn't matter.
Okay, all right. If you're just going to leave it open, I'm just going to go easy weasy, lemon squeezy peasy. That'd be 16 over 3.
Yeah, you...
Dang it. Did I mess up the tablet?
Yeah, you did.
Shoot, a monkey. My bad, K-Steve. My bad.
This technical difficulty brought to you once again by Mr. Hazelwood.
Why? Why once again?
No reason.
That would imply that I've been the cause of other technical difficulties. Maybe we won't be speaking the rest of the lesson. I'll just...
And I could do natural log instead. I don't know. I don't really have a preference personally.
Not speaking.
And, this could be tricky to type in if you're not being careful. You could change that to a 0.5. That might be easiest instead of putting in a fraction.
The answer will surprise you.
It did actually surprise me a little bit.
Not Steve, I'm telling the children.
Wow, -1. Okay, go. You can tell them whatever you want.
You guys are all brilliant. All of you. Thank you for watching.
All right, example 5. You know what I'm looking forward to?
Swine Week?
Swine Week. Swine Week's next week.
Yeah, me too.
As of when we're recording this, it could, when you're watching it, perhaps be the actual week.
Or
right?
it could be way past, depending on viewing history.
Yeah. So
and if you're not one of our students and you're somewhere else, then you're missing out on the glory that is.
Yeah. So there's a website. You could look it up.
It's possible next week's videos I could have a different hairdo. Quite
possible. Or we could be dressed funny. Whatever. All right, example 5. Now these are, I would say, the trickiest part of the lesson.
Yeah, these are hard.
But they're not actually. They're not really that hard.
You have to think differently.
Yes, exactly. So we want to describe how to transform the graph of f of x equals the natural log of x into the graphs of the given functions. Sketch the graph and support your answer with a grapher. So what we want to do...
I'll say on this one, sketching them will be difficult.
Yeah.
Anyway.
A little bit.
Yeah, but there are some things that we should be able to see.
Yes.
By hand without graphing.
Right.
Yes.
And so the way we want to start off here is using the change of base formula.
Yep, indeed.
And we have the natural log of x over the natural log of 5.
Now, remember, natural log of x graphs just like all the other fractions and functions and everything else. And so this is not natural log of x over natural log of 5. This is 1 over natural log of 5 times the natural log of x. And that should help us see exactly what's happening with this.
Yes, because now this is either a vertical stretch or a vertical shrink on ln of x, depending on whether or not that number is greater or less than 1.
Right.
Off the top of your head, do you know?
No, I'm going to say probably bigger than 1.
So it says I mean, obviously we would want to do this without graphing it on our calculator at first, but you would be able to probably...
Ooh, I was right. 1.6, baby. It's less than 1 because it's 1 over that.
Okay, so natural log of 5
I was partially right.
is...
I knew the natural log of 5 was larger than 1, but 1 divided by that is less than 1, which means that we have a vertical squishing.
This is a vertical shrink of...
Natural log of 5, actually.
Well, of 1 over natural log of 5. Or 1 over 1.609, right. Or you could divide that out and see what that is.
I can whip that up real quick.
So
0.6213.
So now, really what's important is you've got to get the hang of what the natural log and all these other logarithmic graphs look like. They all are going to start at 1, 0, unless there's a shift.
Right, but there is no shift in this case because we're not adding or subtracting any numbers anywhere.
Right, so if it shrinks, it's basically going up about half as much. Well, that's really difficult to show on a graph.
Right.
So,
which is why I said at the beginning that actually graphing these by hand could be tricky. But if you were to graph natural log of x and then graph 1 over natural log 5 of natural log x, you could see a difference.
You should see a difference. And this is really, to me, the important part, this work that we did to get here.
Yes.
That's the really important part of this problem.
Right.
So let's try another one.
Okay.
So this is natural log of x over natural log of 1/4. I feel like the fact that this is a fraction may end up giving us a different result.
Yes, I agree with that 100%.
Because now we've got 1 over the natural log of 1/4 times the ln of x. And what is 1 over the natural log of 1/4?
Well, I believe that's going to be negative natural log 4.
Okay, which is what?
Well, if you'll just give me a second to punch it in instead of rushing me, because I don't work well under pressure.
Okay.
Negative 1.3863.
Say it again. Negative
1.3863. That's what's in the denominator.
So we have a negative, which means that this is a reflection across the x-axis.
Oh, I was right.
And 1 over 1.3. Congratulations. Are you going to do 1 divided by that or no? Okay, this is a vertical shrink.
It's cabbage patch. It's cabbage patching. I got you right now. Negative 0.7213. Got that right.
Or actually, it's not a shrink with that negative.
No, the negative can't be there for the shrinkage. But it would reflect over the x-axis that way.
Yes, that's why I wrote reflect across x-axis.
Yes.
Yeah. And so if we graph this, this is a little trickier. I'm going to graph this over to the side of our faces, not on top of them.
I'll just double check you because this one is a little tricky.
Okay, 0 or 1, 0. That's our starting point normally. We are reflecting across the x-axis, so that moves it this way, which means it still stays where it's at. And then we are shrinking, but it's going to go this direction and this direction. Think about basically, these are actually really close to each other, right? Except that this one's flipped. So think about flipping this right here. Well, it looks kind of like what I drew there.
Yeah.
So
should be similar.
Yep, that's all there is to it.
There you go.